Hello, I'm Fer, and today we are going to learn about the Fourier series. So, the Fourier series were discovered by a guy called Jean-Baptiste Fourier in the 18th century. So Fourier was born during Fourier was born during the time of the French Revolution. Yeah, he even fought in the French Revolution. In the side of the revolutionaries, he was actually he fought in Napoleon's army. He was his scientific advisor during the campaign of Egypt. He was later appointed the governor of a region of France, so he had quite a good political career. But he was also a scientist. He was very interested, especially in how heat flows, how heat moves from one place to another. And you may think that that's quite a trivial problem. I mean, of course, heat moves from where it's hot to where it's not hot, all right? But and people knew that. I mean, people knew that things that are not cold, heat cold things up. But that wasn't the whole story, because people had made experiments that the flow of heat was more complicated than that. There was more to it. So Fourier wanted to find out. He wanted to explain how heat could move from one place to another. And so in doing that, doing some physics, he derived the heat flow equation. And the heat flow equation is this. I'm going to explain it in a moment. So if U is a function that tells you the temperature of an object in space and time, so U is a function of x, y, c, and t, all right? And the flow of heat always satisfies this condition. And if you don't know what this weird triangle means, it's just an operator called the Laplacian, which is just a short way of writing the following: the double derivative with respect to x plus the double derivative with respect to y plus the double derivative with respect to c. But this is too long to write, so we just write a triangle with a square over it. All right. So this is the heat flow equation. But this is, and you may think, oh, well, so Fourier solved it. No, because getting the equation is the easy part. But this is a differential equation, and you have to solve it to get to know how heat flows in some situation. If you are familiar with differential calculus, and if you're learning about Fourier series, I assume you're a little familiar with differential calculus, you probably are thinking of how you are going to solve this. So let's solve this. And let's solve this for it's a very simple example. You may think that it's that is not something that you might find in the real world or whatever, but doesn't matter. It's just an easy example to analyze. So let's say that we have the blade of a sword, all right? Here's the blade of a sword, and we put ice on the extremes. It's just a bunch of ice, so that its temperature in its extremes doesn't change, and the sword itself has a length of L. I don't know what it's L, a meter, whatever. And and we want to know how the heat flows in this sword. Well, the first thing that we notice is that, the ice, we are assuming that the ice is so much and so cold that the temperature in the tip and in the bottom of the blade is going to remain constant. And we are going to call this constant 0, because, we can call it whatever. I mean, temperature scales are really arbitrary anyway, and really all measurement is rather arbitrary, how you measure it, but whatever. So we are going to call this point x equal to 0, and we are going to call this point x equal to L, and this function is going to be just unidimensional. So this is useful, because then we are going to just use this part of the Laplacian, because since the function doesn't depend on y nor c, its derivative is already 0 in those cases. So the function in 0 and at all times is equal to 0, and the function when x is equal to L at all times is also equal to 0. And we have one more initial condition for this function, that this function in all space at the beginning at time equals 0, this is just going to be equal to x. Yeah, I don't know how someone made that the distribution of heat was that at the beginning. Maybe they were playing with a lighter very carefully around it in order to make it have that precise distribution of temperature. It doesn't matter. Let's just, as I say, just a useful example to analyze. All right. So the first thing to do is to assume. Let me go here. Here. So let's just assume separation of variables, all right? And I'm gonna write the function again. Oh, I had forgotten the first time I wrote it that there should be a constant here called alpha, because different materials, the heat flows at different velocities. They don't heat at the same rate, whatever. So we have this function, all right? And then now, let's just go ahead and solve it. And the first thing that we should do is assume separation of variables. I'm going to assume that u is made of two functions, one called x that only depends on x, and one called t that depends only on time. All right. So let's write it. Let's go ahead and write like the double derivative with respect to x of x times t is equal to alpha plus times the derivative with respect to time of the same function. All right, of times x. The order doesn't matter. And well, the first thing that you notice is that t doesn't depend on x, so we can take it out of the equation. And the same here, x doesn't depend on t, so we can take it outside of the, well, not the equation, the integral, sorry. We can take it outside of the integral. The derivative, sorry, I don't know what's happening to me. Well, I don't know what's happening, all right. And it would be nice if we have everything that depends on x on one side and everything that depends on t on the other. So I'm going to divide everything by the same function, yeah? By u, x and t. So this is going to cancel t here and this cancel x here. And I'm going to end up with 1 over x times the double derivative with respect to x is equal to alpha over t times the derivative with respect to t. All right? And another way to write this is just, let's take everything to the same side of the equal sign. And it ends up being sort of like this. This is all equal to 0. But this is rather suspicious, isn't it? That we have completely different equations, functions being derivated in different ways with respect to different functions, and yet they happen to be the same at all points? No, I don't believe that. It's very unlikely. I mean, the only way that could happen is if both were constant. And probably they are. Probably this is equal to some constant c, and probably this is equal to some constant c. Well, here minus sign. C and minus c. Oh, so that makes sense. Interesting. So then why are we? So then we can just if they are equal to constants, then we can simply do the following. I can just take this one and I know that alpha over t times the derivative in time of t is equal to minus c. All right, like this cancels the minus signs. You should probably have done, you have probably done many examples like this in your differential calculus classes. And the thing that I want to do is that I'm going to multiply by dt over alpha in both sides, right? So that this is going to get cancelled here and here. And so I end up only with dt over t is equal to c plus dt over alpha. All right. So see, I can integrate both sides actually. See? And for example, this is a rather simple integral. It's just the natural log of t. And this is just all. These both are constants, so I just have c over alpha plus t plus c. Nice. And now what? Well, I don't want t. I don't want the natural log of t. But then I can just take e and raise both sides by e. And here e cancels the logarithm. So I just end up with t is equal to, well, here this doesn't simplify much more, but now here the integration constant that I messed up with the parenthesis sign over there. This should be plus some, just c1, just to not confound. There's no confusion with this other c. And here I just have e to the c1, but e is a constant, c1 is a constant. So let's call this whole constant just a times a to the c times t over alpha. Oh, that's rather nice. So we have the part time. We have the part of u that depends on time. Or have we? Because when you think about it, this makes absolutely no bloody sense. Just think about it. Like, think how is how are the exponential functions? If you have t, just exponential functions grow, and they grow a lot. Population, interest, whatever, they grow, and they grow a lot. So this couldn't be temperature, because we know that temperature doesn't behave like this because we are alive, because temperature doesn't grow infinitely, but rather reaches equilibrium, like in the example with the ice cube in the glass of water. So what is happening here? Well, this is not the only kind of exponential equation that there is. This is e to the x, but this is also an exponential equation, and this is e to the minus x. So this is probably what is happening in this case. So who is the negative? So let's assume that alpha is not the negative thing, but because it's a constant of the material. But what can be negative, and time is obviously never negative because time runs forward. But what is negative is actually c. C was lower than 0, and we didn't know it until now. It's just like when x is equal to minus 4. I mean, just because it didn't have the negative sign, it didn't mean that x wasn't negative, right? So it would be convenient to write c in terms of something else. So c is a negative number. So let's write it as negative k squared. And why am I using just a number squared? Well, because if it's a number and it's a square, I'm pretty sure that it's a positive number, unless it's imaginary numbers, but we are not dealing with imaginary numbers right now. So I'm pretty sure that k squared is something positive, and with this minus sign, I'm pretty sure that it's something negative. So t is equal to a times e to the minus k squared times t over alpha. And that's it. And now what? Well, now I think I am running actually out of time. So in the next video, I'm going to solve the part of the heat equation that depends, of the heat function that depends on the distance. And if we are lucky, we are even going to get onto how to get the actual solution for the heat equation, the whole solution.